somewhere above the lunar surface, a spacecraft the size of a small car is closing in on an empty stretch of terrain near a crater named for Albert Einstein. It has no fuel left for 18 months. 2 minutes out, a second spacecraft, this one still under control, slides into a pass just a few kilometers away. Engineers on the ground in South Korea have planned this moment for weeks. Their spacecraft, Danuri, aims its cameras at the tumbling dead object ahead of it and starts recording. Neither object is alive in any meaningful sense. One is a rocket stage that ran out of purpose the moment it did its job. The other is a robot taking its photograph, on purpose, as it falls. At 6:35 Universal Time, the dead one hits. Ground-based observatories in New Mexico, Arizona, and Chile are already watching. Spectrometers are recording light. Somewhere in that light, sodium and lithium gas begin glowing in a plume rising off the lunar surface, chemical signatures of a collision, evidence that something from Earth has just become permanently part of the Moon. This has happened before. It will happen again. And after almost 70 years of doing this, we are only now starting to understand exactly what we're doing when it does. The object that struck near Einstein Crater on the morning of August 5th, 2026, has a name, 2020-5010D. It is the spent upper stage of a Falcon 9 rocket, and unlike almost everything else that has ever hit the Moon, we know exactly what it was. We know its mass 4,900 kilograms. We know its length 13 meters, roughly the height of a 5-story building. We know where it came from and why it was up there in the first place. On January 15th, 2025, that Falcon 9 launched 2 commercial moon landers, Firefly's Blue Ghost and ISpace's Hakuto-R, known as Resilience, on a trajectory toward the Moon. To get them there, the rocket's upper stage fired its engine one final time, accelerating to roughly 10.9 kilometers per second. That single burn, called a trans-lunar injection, used up essentially all the propellant the stage had left. Once the landers separated, the stage kept moving. It had no fuel to bring itself home. For the better part of 2 years, it looped through the space between the Earth and the Moon, pulled along by a mixture of solar pressure and gravity, until that combination finally aimed it at the lunar surface. By early 2026, an independent astronomer named Bill Gray had been watching it the whole way. Gray runs a piece of tracking software called Project Pluto, and over 18 months, he and a network of observers collected more than 1,000 separate measurements of the object's position. Long before NASA made any official statement, Gray's data said the same thing. This stage was going to hit the Moon, near Einstein Crater, at approximately 6:35 Universal Time on August 5th. He was right down to the minute, which is its own kind of achievement, given that nobody was steering. Here is where the story gets its first real complication, because this was not the first time a rocket stage was known to be heading for the Moon, and the last time everyone was wrong. In 2015, the Catalina Sky Survey picked up a faint, unidentified object drifting through Earth's orbit and gave it a placeholder name, WE0913A. Observers eventually connected it to a Falcon 9 that had launched NASA's Discover spacecraft that same year, and for the next 6 years, that identification simply sat there, unquestioned, filed away as settled. Then, in late 2021, astronomers realized WE0913A was going to hit the Moon on March 4th, 2022. Suddenly, a minor cataloging detail became global news because the assumption on record was that a SpaceX rocket was about to leave a fresh scar on the lunar surface. Then, an engineer named John Giorgini at NASA's Jet Propulsion Laboratory looked closer. He noticed something that should have been obvious years earlier. DSCOVR's actual flight path never took it particularly close to the Moon. Whatever WE0913A was, it almost certainly wasn't the DSCOVR upper stage. Gray went back through his own data. Tracing the object's orbit backward, he found a lunar flyby in February 2015, and before that, another one in October 2014, lining up almost exactly with the launch of China's Chang'e 5T1 mission on a Long March 3C rocket. A researcher named Jonathan McDowell added a piece of corroborating evidence: a small secondary payload. A ride-share experiment that had been bolted to that Chinese booster had trajectory data that matched perfectly. The identity of the object changed in public days before it hit the moon. China's foreign ministry disputed the identification, saying the booster in question had already burned up in Earth's atmosphere years earlier. The United States Space Command checked its own tracking records and confirmed the opposite. The stage in question had never re-entered. What actually crashed into the moon on March 4, 2022, near a crater called Hertzsprung, is now generally accepted by the people who tracked it to be that Chang'e 5T1 rocket body object of disputed ownership, unconfirmed by the country that most likely launched it, understood only through the patient, unglamorous work of astronomers cross-checking each other's math. No human-made object has ever struck the moon under conditions as well documented as the one that hit near Einstein Crater in August 2026. That single fact is worth sitting with for a moment, because it's the reason this particular impact matters more than its size would suggest. For the first time, scientists on Earth not estimate, not infer, but know the exact mass, shape, and material of something about to strike the lunar surface. That was never true before, and it will shape everything that happens next. To understand why an old rocket stage ends up wandering the Earth-Moon system for a year and a half with nowhere to go, you have to understand a very unglamorous piece of orbital mechanics: the price of coming home. A standard Falcon 9 upper stage, after a routine mission to low Earth orbit, disposes of itself with a small engine burn that tips it back into the atmosphere, where it burns up completely. That maneuver is cheap. It needs only a small amount of leftover fuel. But a stage that has just performed a translunar injection, the burn that sends a spacecraft toward the moon, is in a completely different situation. To bring itself back to Earth's atmosphere afterward, or to push itself into a stable orbit around the Sun instead, would require another burn of comparable size to the one that sent it moonward in the first place. That much propellant has to be budgeted from the very beginning of the mission, built into the design before the rocket ever leaves the pad. By the time 20.50.10D separated from its two lunar landers, that propellant simply didn't exist. It had all been spent getting the payloads where they needed to go. As Juliana Scheiman, director of NASA's Science and Dragon programs at SpaceX, put it at a NASA briefing days before the impact, what put the stage on its final path toward the moon was essentially a mixture of solar activity and gravity forces. In plain terms, nobody aimed it. Physics did. This isn't a flaw unique to one company or mission. It's a structural reality of translunar trajectories. Disposing of a stage safely afterward costs about as much fuel as getting it there in the first place, and a mission that wasn't designed with that cost in mind has no cheap way to fix it later. SpaceX has already demonstrated the alternative works. In November 2025, a Falcon 9 stage that launched the Escapade spacecraft was given extra propellant specifically so it could perform a controlled burn into a solar orbit after separating from its payload, deliberately avoiding exactly the kind of drift that led to the August impact. And the broader numbers back up a shift in practice. Between 2024 and 2025, the share of Falcon 9 stages left on orbit after their missions fell from 13 out of 134 launches to just 3 out of 165. That improvement is voluntary. Nothing currently requires it. And that quiet fact that the safest option exists, works, and simply isn't mandatory sits underneath everything that follows in this story, all the way to the very end. By the time 2025 010D reached the lunar surface, it was traveling at approximately 8,700 kilometers per hour, roughly 7 times the speed of sound in Earth's atmosphere. Though the moon has no atmosphere to slow anything down or spread the impact out over time, the kinetic energy released was equivalent to roughly 3 tons of TNT, delivered all at once, with no air resistance and no thermal burn-off to soften the blow. NASA's Meteoroid Environments Office at Marshall Space Flight Center predicted a resulting crater approximately 18 meters wide and 4 meters deep. A separate model, the Hybrid Optimization Software Suite, built by scientists at Los Alamos National Laboratory specifically to simulate hollow, human-made objects striking the moon, predicted something slightly larger. A crater between 20 and 30 meters wide, roughly 5 meters deep, throwing an estimated 1.1 million kilograms of lunar regolith into the surrounding terrain. 2 competing predictions, 2 different numbers, and a very specific plan for finding out which one is closer to the truth. NASA's Lunar Reconnaissance Orbiter has been circling the moon at roughly 100 kilometers altitude since 2009. Its narrow-angle camera can resolve details as small as about 50 centimeters per pixel, sharp enough to image an 18-meter crater with something close to surgical precision. LRO photographed the Einstein Crater region before the impact, establishing a clean baseline. In the following weeks, it will pass over the site again and photograph what's actually there. Whichever prediction comes closer, NASA's estimate or the Los Alamos model becomes something engineers can actually use, a validated tool for calculating how close a future lunar base, a future landing pad, or a future astronaut can safely be to a predicted impact zone. If neither matches, every safety margin currently built on these assumptions will need to be revised. Separately, a team at the University of Texas at Austin modeled what the impact plume itself should look like, not the crater, but the cloud of debris thrown upward in the instant of collision. Their prediction: a central spike of ejecta rising 75 to 100 kilometers above the surface, spreading laterally as far as 183 kilometers, and remaining, for the first few minutes, dramatically brighter than the dark sky around it. The impact flash itself, the literal moment of collision, was expected to last less than 1 second. Researcher William Joe, who led that modeling work, put it bluntly beforehand. Most observers, he warned, would watch for the flash, miss it in under a second, and never bother tracking the plume that followed, even though the plume was where the real science was waiting. That warning turned out to matter, because within minutes of the impact, telescopes far from the flash's location, including the very large telescope in Chile, picked up exactly what Joe had described. Not the flash, but the aftermath. Emission lines of sodium and lithium gas, glowing in the expanding cloud above the crater, lasting 5 to 10 minutes before fading. The sodium most likely came from lunar soil, thrown loose by the impact. The lithium most likely came from the rocket stage itself, a chemical fingerprint of the object that made it still visible for a few minutes against the black lunar sky. Sodium, specifically, is not a new character in the story of the moon. Scientists have known since 1998, when researchers at Boston University spotted it during a Leonid meteor storm, that the moon trails a faint tail of sodium gas hundreds of thousands of kilometers long, streaming away from the surface. NASA's LEDI mission spent 7 months in 2013 and 2014 studying exactly this, watching sodium and potassium rise off the lunar soil during meteoroid showers. That earlier research is part of why scientists watching the August 2026 impact knew what they were looking at almost immediately. The glow in that plume wasn't a mystery. It was a known signature, produced by a known process, only this time triggered by a rocket instead of a rock. It's worth remembering, at this point in the story, that in less than 2 years, human beings are scheduled to be standing on this same moon again. That fact will matter more later. For now, it's simply true. sitting quietly in the background of everything else that's happening. Every rocket stage that has ever hit the moon has told a slightly different story in the shape of the hole it leaves behind, and some of those shapes still don't add up. Start with the double crater near Hertzsprung, left by the misidentified Chang'e 5T1 stage in March 2022. When the Lunar Reconnaissance Orbiter finally located the site in May of that year, it found not one crater, but two an 18-meter crater directly overlapping a 16-meter crater, forming a shape unlike anything seen from a previous rocket impact. Bill Gray, who tracked the object in, ruled out the obvious explanation first. The stage came in at about 15 degrees off vertical, close enough to a straight-down impact that a shallow, glancing angle couldn't explain the double shape. Mark Robinson, principal investigator for the LRO camera team, offered another possibility. A spent rocket typically carries most of its mass at the engine end, with the rest being empty tank. A double crater like this one, he suggested, could mean the object had a second concentration of mass at the opposite end, something heavy bolted to the front, alongside the usual engine weight at the back. We know the Chang'e 5T1 stage did carry a small secondary payload on its nose, two scientific instruments weighing a combined 14 kilograms, part of a commercial mission called the Manfred Memorial Moon Mission. But 14 kilograms is a small number. By itself, it doesn't obviously explain a second, nearly equal crater. So the double crater remains what it has been since the day it was found, a hypothesis, not an answer. Some researchers believe there was undisclosed hardware on that rocket body that nobody has ever accounted for. Others simply note that we may never know for certain, because the country that most likely launched the object has never officially confirmed it was theirs, never published its mass, and never disclosed what, if anything, rode along at the front. Compare that to what happened decades earlier during the Apollo program, when rocket disposal was deliberate rather than accidental. Between 1970 and 1972, NASA intentionally crashed 4 spent Saturn V third stages, called S-IVBs, into the moon, on purpose to generate seismic shock waves that instruments left behind by earlier astronauts could measure. Each stage weighed around 14,000 kilograms and struck at roughly 2.6 kilometers per second, slower than 5010 but far heavier. None of those 4 Apollo impacts produced a double crater. Instead, they produced something else strange. Shallow, irregular, elongated craters, unlike the deep, round shapes left by natural meteorite strikes. Researchers later described the effect almost affectionately, like an empty soda can hitting the ground. Nearly all of an SVB's mass was fuel, and by the time it struck the moon, the fuel was gone. What was left was mostly hollow shell, crumpling on impact rather than punching cleanly into the surface. One of those 4, the Apollo 16 stage, took 43 years to find. Contact with it was lost briefly during its final descent in 1972, and when the Lunar Reconnaissance Orbiter finally located the crater in 2016, it was roughly 30 kilometers away from where 1970s-era tracking equipment had predicted. The Apollo impacts weren't purposeless collisions. They were instruments. The seismic waves they generated helped scientists measure the structure of the moon's interior using rocket stages as, essentially, calibrated hammers striking a bell whose ringing told researchers what the inside of that bell was made of. At the time of the Apollo 13 impact, only one working seismometer existed on the moon, deployed 5 months earlier at the Apollo 12 landing site, roughly 135 kilometers from where the falling stage was expected to strike. Wrapped in protective foil against the moon's extreme temperature swings, it recorded the arriving shock waves in data researchers are, remarkably, still studying today. Because the exact time, location, and mass of each Apollo impact was known so precisely, these 4 craters have become something closer to a laboratory than a historical footnote. Researchers have since rebuilt the S-IVB impacts inside modern shock physics simulations, testing different possible shapes for the hollow, irregular booster to see which one produces a crater matching what was actually photographed. What the data suggests is that the crater's odd, lopsided shape is best explained by the booster's own irregular, low-density structure, not by anything unusual in the ground it struck. The same simulations are now being adapted to help interpret seismic data from Mars, where a NASA lander has listened for meteorite impacts since 2018 without ever confirming one. 50 years later, the Apollo craters are still teaching us how to listen to a planet. Not every deliberate lunar impact was about seismology. In 2009, NASA intentionally crashed a spacecraft called LCROSS, along with its own spent Centaur upper stage, into a permanently shadowed crater near the lunar south pole, specifically to kick up debris that could be analyzed for water ice. It found it. And in 2014, a small NASA orbiter called LCROSS, after months of studying the moon's extremely thin, dust-laden atmosphere, was deliberately steered into the lunar far side, striking near a crater called Sundman V at roughly 5,800 kilometers per hour. Mission planners chose the far side on purpose, specifically to avoid any risk to the historic Apollo landing sites on the near side. Every one of these impacts, accidental or intentional, identified or disputed, has added one more entry to a strange, growing catalogue. Craters made not by the universe, but by us. Since the Soviet Union's Lunar, too, became the first human-made object to reach the moon, on September 13, 1959, an estimated 209 metric tons of material from Earth has accumulated on the lunar surface. Landers, impactors, rocket stages, equipment left behind by astronauts. All of it's still there, because there is no wind, no rain, and no erosion on the moon to ever wear it away. To put the August 2026 impact into scale, 20-5010D at 4,900 kilograms struck an empty stretch of terrain roughly 900 kilometers from the nearest other structure on the lunar surface. It was harmless. Nothing was near it. Nothing was ever at risk. But that comfortable distance is not a permanent feature of the moon. It's a temporary condition of an era that is already ending. More than 100 lunar missions are planned over the next decade alone, according to an assessment by the Aerospace Corporation, from government space agencies and commercial companies around the world. Every one of those missions will need to get to the moon, and many of the rocket stages that carry them there will face the exact same fuel budget problem that put 20-5010D on its collision course. Jonathan McDowell, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics who tracks human-made objects across the solar system, summarized the situation with a kind of careful precision that avoids overstating the danger while still naming it clearly. This particular impact, he said, wasn't a problem. But in a future with long-term bases on the moon, similar impacts would be. The lesson he drew wasn't about this one rocket stage. It was about the habit of leaving rocket stages in chaotic, unmanaged orbits at all. And that future is closer than the calm tone of that warning might suggest. In April 2026, just months before 2025, 010D struck near Einstein Crater. 4 astronauts flew a circumlunar mission called Artemis 2, looping around the moon and returning safely to Earth. It was the first time humans had traveled to lunar vicinity since Apollo 17 in 1972. NASA is currently targeting early 2028 for Artemis 4, the mission intended to put astronauts back on the lunar surface itself. 2 years. That's roughly the gap between the impact this documentary opened with and the moment human boots are scheduled to touch lunar soil again. Here is what makes all of this more than a story about one old rocket stage. There is currently no binding international rule that requires anyone to prevent this from happening. The Artemis Accords, a set of principles for behavior on and around the Moon, signed by 70 nations, address cooperation, safety zones, and protection of historically significant sites, like the Apollo landing areas. Post-mission disposal is even named as a topic worth addressing, in what's called Principle 12. But naming a topic and requiring an action are different things, and nothing in the Accords legally obligates any signatory to dispose of a spent rocket stage responsibly. In the United States, the Federal Communications Commission adopted a new licensing framework for cislunar spacecraft in July 2026, a formal category for commercial missions heading toward the Moon. It includes no disposal requirement for the upper stages that get those spacecraft there. Separately, the Federal Aviation Administration had proposed a rule specifically addressing upper stage debris back in 2023. It withdrew that proposal in January 2026, citing a need for further study after industry raised concerns about cost. Researchers at the Belfer Center noted, as recently as 2026, that there is currently no single agency clearly tasked with regulating the removal of debris in cislunar space, the region between Earth and the Moon, that an increasing number of missions now have to pass through. The only truly international guidelines that currently touch lunar disposal at all come from COSPAR, and even those exist for a completely different purpose: preventing biological and chemical contamination of scientifically sensitive sites, mainly near the lunar poles. They were never designed to govern where an out-of-fuel rocket stage is allowed to fall. There is also a transparency problem underneath the legal one. Artemis Accords signatories have agreed to submit registration information to the United Nations Office for Outer Space Affairs, including plans for post-mission disposal. In practice, NASA has often listed that specific field as defer to commercial provider in its own lunar mission registrations, without yet building a formal channel for commercial providers to submit the missing information themselves. Legal analysts at Clyde & Co. reviewed the state of lunar governance in April 2026 and concluded, plainly, that space debris remains governed largely by voluntary standards rather than binding law. Some mechanisms for accountability do already exist. NASA requires an orbital debris assessment report from its own contracted missions, obligating a disposal plan before launch, a workable model already sitting inside the agency, just not yet extended industry-wide. Internationally, bodies like the Interagency Space Debris Coordinating Committee include China and Russia alongside the United States, which matters, since any workable cislunar standard will eventually need buy-in from every country capable of reaching the Moon. Even so, current guidance from groups like the IADC has a well-documented gap in exactly this region, the space beyond Earth orbit, where rules built for satellites circling close to home simply stop applying. This isn't a story with no one paying attention. The UK Space Agency has commissioned research comparing disposal options for spacecraft in different lunar orbits, assessing controlled impacts, transfers to orbits around the Sun, and other alternatives for which options carry the lowest risk and cost. Japan's space agency, JAXA, has funded a private company, iSpace, to study how the commercial sector views the debris problem. South Korea has hosted multiple international discussions specifically on coordinating traffic in cislunar space. The Aerospace Corporation has warned that a single serious collision in this region could scatter debris that lingers for thousands of years, because, unlike low Earth orbit, there's no atmosphere out there to eventually drag the wreckage down and burn it away. The tools for solving this escapade proved a controlled disposal burn works. Purdue researcher Carolyn Frewer put the underlying philosophy simply: everywhere humans have gone in space, we have left debris behind, and the fewer pieces we create, the smaller that problem becomes down the line. Even the process of gathering better data has, until recently, been left to whoever happened to be watching. South Korea's Danuri orbiter captured its close flyby of 20-5010D using a lunar terrain imager and an instrument called ShadowCam sensors, originally built to peer into permanently dark polar craters, repurposed on short notice to photograph a falling rocket instead. Newer, standardized instruments are beginning to change that improvisational pattern. A sensor suite called SCALPS has been developed specifically to record how a spacecraft's engine plume interacts with lunar soil during landing, data that's been strikingly hard to gather consistently across different missions, encouraging operators to share what instruments like it record through venues like the UN's Committee on the Peaceful Uses of Outer Space and the Artemis Accords themselves, is one of the few concrete steps researchers agree could move the governance conversation forward, not by creating a new rule, but by making sure everyone is finally working from the same facts. What's missing isn't a solution, it's a requirement. So why do we keep crashing spacecraft into the moon? Some of it is deliberate, and has been from the beginning. Apollo's engineers wanted seismic shockwaves to study the moon's interior. LCROSS's team wanted a plume of debris to search for water. Laddie's controllers wanted a clean, harmless ending for a spacecraft that had already finished its job. Every one of those impacts was a choice, made by people who understood exactly what they were doing and exactly what it would cost. But a growing share of it isn't deliberate at all. It's the quiet, physics-driven consequence of a decision made or not made years earlier, at the design stage of a mission, long before anyone was thinking about where a rocket stage might eventually run out of options. 20-50-10D didn't fail. It didn't malfunction. It did exactly what it was built to do, used exactly the fuel it was given, and then simply had nowhere left to go but down. We now have, for the first time, an impact we understand almost completely: mass, shape, composition, trajectory, timing, all confirmed before it ever struck. In the coming weeks, when the Lunar Reconnaissance Orbiter photographs the fresh crater near Einstein Crater and compares it against two competing predictions, we'll learn whether our models of how hollow, human-made objects behave when they strike another world are actually correct, or whether, like the fuzzy history of that double crater near Hertzsprung, this too will turn out to hold something we didn't expect. Bill Gray, the tracker who called this impact months in advance, down to the minute, described the broader pattern in blunter terms than most scientists allow themselves. This, he said, is a kind of carelessness, not malicious, not even particularly unusual, just an old habit that space agencies and companies have never quite been forced to break. For nearly 70 years, the moon has absorbed everything we've sent its way without complaint. Every deliberate impact, every accidental one, every misidentified rocket body eventually traced back to its source through nothing but patient orbital math. It has no wind to erase the record. Whatever lands there stays. In less than 2 years, for the first time in over half a century, human beings are scheduled to walk on that same surface again onto ground that is quietly, permanently accumulating the debris of everything we've already left behind, with no rule yet written that says how much more of it is allowed to fall, or where. We tracked the object, we predicted the impact, we photographed the plume, measured the sodium, calculated the crater. And in doing all of that, so precisely, we finally built a record clear enough to show us something we couldn't see before. How much of this was never actually a decision at all, and how little time we have left before that starts to matter.